Okay, next up is group.
Can everyone see my screen?
Yeah, can.
Can I begin?
Please go ahead.
Okay. Good evening, everyone. Today, my group 3, will be presenting on our project, KMode. For our presentation, we'll be going through the intro, EDA, modeling, and lastly, followed by our app. We know that the IMO intends to reduce carbon emissions by 40% by 2040. So what's stopping us from achieving such goals? To begin off, I'll be sharing the 4 key pain points faced by our current stakeholders. First is time loss from the manual process of data entry of ship logs. Second is the incorrect data as a result of having manual touchpoints. Third is communication as a result of having different units in different locales. Fourth is the lack of baselining, as ship owners do not know how to set achievable targets to hit the required goals by 2040. From this, we develop our problem statement to deliver well-curated, specific emission profiles using data-driven solutions in order to achieve competitive reductions in carbon emission. Our data was prepared as follows. We begin off by performing data cleaning, such as standardizing values in columns, value imputation of empty values, and removing outliers. We then perform web scraping via vesselfinder.com to obtain more ship features, such as gross tonnage, summer date rate, as well as ship age. These fields are important because they form the annual efficiency ratio, AER, from which the carbon intensity indicator, abbreviated CII, is derived from. The CII is also what we're trying to profile and set baselines for. Hence, the inclusion of these features gives us more specific information to build profiles with. Then, we perform a merge to combine our clean dataset with the web script data. Next, why perform clustering? Firstly, the naive approach of trying to profile by ship type is not sufficient. For our goal of trying to profile ships based on CO2 emissions, we notice that within ship type, there are significant differences between the top emitters of CO2. This is due to the significantly differing usage of the ships. For example, the RoPax ship on the right can be used to ferry vehicles, cargo, or passengers. Similarly, passenger ships can be as big as cruisers and as small as yachts. Hence, profiles must be formed based on selected features describing their specific use cases so as to rigorously profile them appropriately for the intended purposes of building profiles for carbon emission. Secondly, by observing the 3D plot of the quantitative variables, we're able to observe multiple clusters that exist for the same ship type, such as Ro-Ro ship in red. Using the correlation plot, we also observe that the annual average CO2 column is highly correlated with annual average fuel, while gross tonnage is highly correlated with summer date rate. Since highly correlated features do not contribute to differentiating clusters in KMode, we decided to drop annual average fuel column and gross tonnage column. Moving on to Vincent.
Thank you, Renzong. Now I'll be talking about the model our group used to come up with the baseline emission profiles. The first step to our model is to apply KMode's clustering to our dataset. The reason we use KMode's clustering instead of K-means is simply because we have categorical variables which K-means isn't able to work with. KMode's clustering is first used to group similar ships together before we do a further look into how the ships can further improve their carbon emissions. These are the 5 columns which we have selected to be part of the clustering. To find the optimal number of clusters to use, we first plotted the elbow graph. The elbow seems to be around the 5 or 6 clusters area. After trying out both variations, we decided to use 5 clusters as there were no clusters that were significantly smaller than the others. All the clusters have at least 1,000 data points. Here are some of the information about the 5 clusters. The tables on the left give the mean of each variable for each of the clusters, while the graph on the right shows the average CO2 emitted for each cluster. We gave the clusters the names A, B, C, D, or E based on how well performing they are in terms of carbon emission. Cluster 1 has the lowest average CO2 emission, so it is named A, while Cluster 4 has the highest carbon emission, so it is named E. The IMO has plans to reduce emissions by at least 40% before the year 2030, and then by 70% before 2050. We plan to follow this goal and to reduce the emissions from each cluster by this same percentage. We take a look at the annual average CO2 emission value for each cluster, and then look at the 4 quantiles. Taking cluster 0 as an example, the table on the left shows the values for the 4 quantiles. The graph on the right then shows how we can expect each of the quantiles to decrease. The red line has a much steeper gradient to show that it is decreasing at a much greater rate compared to the blue line. The ships that are in the upper quantiles will be required to reduce a larger amount, while those in the lower quantiles will have to reduce less since they are already performing well. By the time we reach 2050, the ships will have improved their emissions such that in overall, this cluster will have decreased their emissions by 70%. Next, Terry will be sharing about the recommended strategies our group has come up with after our findings from the analysis.
Thank you, Ming-Xuan. So we have decided to design a web application to resolve the key pain points plaguing ship owners in their attempts in projecting targets for reducing carbon intensity. Earlier on, we talked about these 4 key pain points. Our solution, ShipMate, aims to address all 4 of these KPIs. Now, let's proceed to a live demo of ShipMate. First, we introduced the first feature of ShipMate, which is to use OCR to address the KPI of time loss. Ship owners can take a photo of the ship logs and upload it to our web app. This will reduce the amount of time to do the manual of data entry and also to reduce data inaccuracy. After taking a photo, ShipMate will use Google Cloud Vision API to process the image. Google Cloud Vision API was chosen as it has the highest text identification accuracy among existing market solutions for OCR. As you can see, the data fields will be filled out by the result of OCR, and ship owners can then do a simple verification to check whether the data extracted is 100% correct. Once done, they can proceed to add this log into our central database. In the back end, before the data is stored in our central database, it is transformed into a consistent format by our automated data cleaning algorithm. This will address KPI number 3 of inconsistent data. The data will also pass through our clustering algorithm, and target setting is done on it. Next, introducing our main feature, which is the dashboard. This comprehensive dashboard provides various information to the ship owner regarding their ship, and it aims to address KPI number 4 of uncertain baseline. Starting from the top right corner, we have the vessel's particulars. Then below it, we have the grade and goals section. Goal shows the 40% and 70% reduction in CO2 the ship has to meet by year 2030 and year 2050 respectively. Grade here refers to the cluster and quantile range that the vessel is assigned to based on our KMode clustering algorithm. Next, suggestions refer to some general suggestions we advise ship owners for them to explore on how to improve their CO2 emission. We also have a countdown feature to inform ship owners how many days are left until the next reporting period. Lastly, based on their grade, we provide a CO2 line trajectory for ship owners to assist them in setting short-term goals to achieve the 40% reduction by year 2030. The gradient of this curve is based on the quantile the ship falls into, as previously mentioned in our model explanation. The long-term projection shows the CO2 emission target for every 5 years, following a linear trend. We will now move on to our prediction feature. Here, ship owners can make use of this feature to add a ship's journey to predict the amount of CO2 it will roughly produce. This is where ship owners can add a trip by filling out the various info. After adding a journey, here you can see on the right the estimated CO2 emission. Through our research, we believe that fuel type can make a difference to the CO2 emission in the short term. Thus, comparing the 8 different types of fuel, we will recommend the best type of fuel type for them to consider switching in terms of both cost and emission factor. However, if the ship owner feels that the additional cost incurred is too high, they can opt to see the next best option up to the 4th best option. So now let's see the 2nd best option. Here we can see that the fuel price is lower for the 2nd best option of LNG, but the CO2 emission will be higher than that of the 1st option of methanol. I'll now end the live demo and go back to the slides. Next, I'll talk about the limitations of our project. Firstly, one limitation was that we were unable to obtain information regarding the fuel used by the ships. The assumption that we made was that all vessels use the same type of fuel. However, this is not the case in real life. After further research, we found that the type of fuel used is related to the amount of CO2 emitted. Therefore, if we have such information, we can provide better recommendations for ships to reduce carbon emissions. Next, our entire project only focused on reducing CO2 emission due to the limitation of the dataset. As there will be a limit of how much CO2 emission can be reduced, reduction of other greenhouse gases can be further looked into, such as methane and nitrous oxide. Lastly, I'll talk about the future works of our project. There could be a platform on ShipMate to share new technologies that will help to reduce carbon emission. This platform would help companies that produce these new technologies, such as solar panels, to advertise their equipment, giving shipping companies the opportunity to explore more innovative solutions to reduce carbon emissions. Another idea would be to have incentives to encourage lower emission. Under the enforcement of a regulatory body, ship owners that consistently meet carbon emission targets or exceed their goals will be granted extra carbon credits. These carbon credits can be sold to ship owners who fail to hit carbon emission targets. This way, ship owners are incentivized to meet targets or exceed them, while those missing their targets are penalized. And with that, I've come to the end of our presentation. Thank you.
Thank you very much. Very nice presentation. I really liked the simplicity, but yet effectiveness of your application, which you presented using something which is freely available. Also, I like the fact that you have looked at from the perspective of incentivizing. It is very easy to identify who are the outliers and not performing and penalize, but using the carbon credit and thinking about giving incentives for those who are performing better and using different fuel types is a very good idea. And I also recognize that you thought about additional greenhouse gas emissions, which is going to be the very next step moving ahead of 2030. So overall, very nice presentation. Thank you very much. Over to you, Karen.
Yes, so yes, group 3, I also think a really good presentation. I like the way how you started with the key pain points, because usually that already starts to get everyone interested in understanding your solution, because you're starting with some pain points. Again, you've also done some web scraping, very good data science practice. I think you've gathered about 4 new extra fields to use for your data analysis. And your clustering was very meaningful in the ABCDE in terms of the average carbon dioxide emissions. So it makes sense if you say A, then I know you've got the lowest carbon dioxide emissions. I particularly liked your implementation of your demo. So the way you went about telling us how it be implemented, you know, upload the photo and you use OCR to gather the data, and you know, the Google Cloud API to to make sure that the data filters into where it's needed to go. Giving the opportunity also for the ship to check the values that they are correct, and then automatically doing the data cleaning. I thought you thought those steps and that information through very well. Very often, data scientists forget about the implementation, and I thought you did that very well. Fuel type, yeah, while we may be able to switch the fuel types or make suggestions to the vessels, I think there's a lot more to that though, because different fuel types may need different, you know, engines, and different costs may also impact that. So it may not be as straightforward. But I liked your way in which you thought about your limitations. So definitely, yes, type of fuel is highly correlated to the carbon emissions, but also bringing to the point that your focus was more on carbon dioxide emissions, but of course there are other GHG gases to consider to reduce. Your future works were also really good in terms of the solar panels, so that was new for this evening, as well as the carbon credits, which is already coming out in the industry to incentivize. You always have to, as Pio said, we always would need incentives in order to get the action from the different vessel management. So I think well thought through project and analysis. Well done.
Thank you, Professor Piyush.
Okay, next up, group 9.